Ladies and gentlemen, welcome to the lecture Organic Synthesis 1, Stoechiometric Organometallics. And of course, a special welcome to Sandra Lee and the webcast team who will video cast the lecture throughout the whole semester. So, this lecture is the first part. And the second part, with the title Catalytic Organometallics, is scheduled for the summer semester. So, now to Stoechiometric Organometallics. When we have a look at the periodic system of elements, and unfortunately in this lecture hall there is no one, then we notice an awful lot of metals. And you might get the impression that it could be some kind of nightmare if you have to choose a metal for your purposes, for your synthesis. On the other hand, the awful lot of metals offers us the opportunity to find a suitable one. And indeed, for, almost any given synthetic problems involving organometallics, you will find some organometallics reagents with the correct properties you need, and moreover, you have the opportunity to trigger the reactivity by adding further ligands. But this is, of course, more used in terms of catalytic organometallics. So, but the possibilities which are imminent in organometallic synthesis makes that so successful. First example. So we have an allylic organometallic species, two substituents here, and we let that react with carbon dioxide, and after hydrolysis, we will obtain either this carboxylic acid or the one with the quaternary center. If the metal is potassium, an allyl-potassium species, we will get a product ratio of 90 to 10. So let's change the metal to a Grignard reagent. In that case, it was found that it will result in a 1 to 99 ratio. Well, somehow this is a rather strange result. Why? Clearly, the organopotassium compound is much more reactive than a Grignard reagent. Nevertheless, the more reactive reagent leads to the thermodynamically more stable product. Clearly, with the Grignard reagent, 99% of the thermodynamically less stable product means this reaction to that product is clearly kinetically controlled. We can explain that if we have a closer look to the structures that are involved. In case of the potassium species, we have a potassium that is coordinated to the allylic anion, well, it is an extremely polar bond. It is a pi complex. Actually, it is a trihapto pi complex, because the potassium is bound to the 3 centers, coordinated to the 3 centers. We can also call it an eta-3 complex. This is a usual abbreviation for that case. So, highly reactive system, and now it is clear that at that terminal carbon we have well, a minor steric hindrance compared to this center, and therefore it is clear that the CO2 can more easily attack at that center, resulting finally in this also thermodynamically more stable compound. On the other hand, the Grignard reagent in this case, the magnesium is more covalently bound to the terminal position. In this case, it is an eta-1 complex or a sigma complex, in contrast to the pi complex in that case. We have with the magnesium the electrophilic center. Magnesium is, as you know, a Lewis acid, while in Grignard reagent usually ether molecules are coordinated to the magnesium, but in equilibrium an ether molecule pops off, giving free that coordination site, and then the CO2 coordinates to the magnesium and through a 6-membered transition state the CC bond is formed. Well, and this is of course the magnesium carboxylate, and after acidic hydrolysis we have the final product. So this example makes clear that it is indeed useful to choose between different metals, because we have clearly different selectivities. The corresponding allyl lithium species is in this case similar it's in between potassium and the Grignard, whereas the allyl zinc behaves, in this case at least, similar to the Grignard reagent. So, a basic concept which is regarded to be rather useful in choosing the right reagents for a synthesis, you know already, is the HSAB concept. Or HSAB principle. And the name, the abbreviation derives from hard, soft, acid, base principle. It was introduced in the early 1960s by Pearson as an extension of the Lewis acid-base concept. So, Lewis, as you know, defines acids as electron pair acceptors while you can use the expression electrophile as a synonym, and a Lewis base is then, of course, an electron pair donator. Or you can use also the word nucleophile. Now to Pearson's extension. He differentiates between hard acids, soft acids, and well, there is of course something in between, medium or borderline acids. And he introduced the same differentiation to the Lewis bases. Again, hard, medium, and soft. So, how did he characterize the expression hard? So, a hard Lewis acid is generally small, has a high charge density, and is weakly polarizable, or I would say hardly polarizable. So, and soft simply is the opposite. Yeah? So, okay, let's draw that to the blackboard. Soft, big, low charge density, and strongly polarizable. Well, I think this becomes more clear if we put on some examples. For instance, a hard acid. So, what is really small, has a high charge density, and is weakly polarizable? The record holder, of course, is a proton. That's it. Yeah. So, H plus. In this category, we have also lithium plus. Could see also magnesium 2 plus and iron 3 plus. Soft. Well, metals in the oxidation state 0 can be nevertheless Lewis acids, but are rather soft Lewis acids. Nickel plus, but also palladium 2, or the silver cation. And medium, well, there we have then iron 2 plus, zinc 2 plus, and copper 2 plus is also regarded as medium. Now to the bases. Fluoride, the fluoride anion is the prototype of a hard base. Hydroxyl anion is also a hard base, although relatively a bit more soft than fluoride. Then ammonia, NH3, well, a hard base. We have a free electron pair, and we have an element there with a high electronegativity. Nevertheless, it is basic. It is more basic than that. That means this is more nucleophilic than that. Yeah? So, all those are regarded to be relatively hard, although of course, NH3 is more soft than a fluoride. And also here, in this category, alcoholates. Medium, bromide. Somewhere here also the chloride I had forgotten. And soft, clearly the iodide, a big anion. Or conjugated anions. Enolate, conjugated systems are big systems, strongly polarizable, should be regarded as soft Lewis acids or soft nucleophiles. Thiolates, phosphines, hydrides are in this category, and what is rather important for us in this lecture, organometallic reagents, alkyl or aryl anions. That means alkyl metal species. So, now to the core statement of the hard-soft acid-base principle. I will write down that core statement. Soft acids react faster and form stronger bonds with soft bases. whereas hard acids will react faster and form stronger bonds with hard bases. Okay. So, what is the explanation? A hard interaction, what could it be? Well, for instance, a lithium plus and an F minus. Reaction of a lithium plus and an F minus would be driven by the electrostatic charge. Okay? So, hard interaction is charge controlled. And two centers with opposite charge, with a high density, will react rather fast with each other if we put aside solvation effects, of course. On the other hand, soft interaction according to this principle is also favored. This is regarded to be controlled by frontier orbital interaction. Well, the first one is easy to understand. The second one you have to think a bit about that. So, for instance, a soft anion. With a soft anion, we have to look at the energy level of the highest occupied molecular orbital. The soft anion has the HOMO on a relatively high energy level. This, I think, is easy to understand. Just take into account the opposite, a fluoride, electronegative. It holds to its electron pairs. The electron pairs of a fluoride are on a low energy level. That means with a soft anion, it has to be the opposite. Okay. A soft Lewis acid or cation HOMO energy level are low, relatively high. Energy level relatively high. So. With a cation, we have to take a look at the lowest unoccupied molecular orbital. This is, of course, the frontier orbital. And in this case, we the energy level of the LUMO is relatively low. Well, for instance, as an example, the allylic cation. Allylic cation are, well, a rather, well, medium or relatively big electron system compared to an H plus or a lithium plus. It is conjugated, it is polarizable. So the allylic cation is a prototype of a soft cation. And because of the conjugation, you have the LUMO in a relatively low energy level. You could easily put on an electron, forming an allylic radical. Okay? So, and the HOMO on a relatively high level, the LUMO of the Lewis acid on a rather low level, that means they have almost the same energy level, and then it's easy to transform electron density. It just fits. Forming then, of course, rather stable covalent bonds. And it's a rather fast reaction. So this model here is called or known as the Klopman-Salem concept. Okay. At this point, let us go back to this core statement. Once again, soft acids react faster and form stronger bonds with soft bases. The expression reacts faster, of course, addresses the kinetics of a reaction and form stronger bonds. This expression addresses the thermodynamics. So, I think this sounds great. With the hard soft acid base concept, we have the impression that we address both kinetics and thermodynamics. This is of course not true. Kinetics and thermodynamics are clearly neglected within the hard soft acid base concept. We just don't differentiate between kinetics and thermodynamics. And well, this is clearly an oversimplification. And that's the reason why a lot of chemists are not in favor of the hard soft acid base concept, and I think the best review article criticizing this concept was published about 2 years ago by Herbert Meyer from the LMU in Munich, and it was published in Angewandte Chemie International Edition 2011 on page 6470, and it's about 35 pages long. And the article has the interesting title, Farewell to the HSAB Treatment of Ambient Reactivity. Well, very interesting article, and he is right in a lot of points. However, if you use the HSAB concept as some kind of qualitative guideline, as some kind of rule of thumb, it will help a lot and still makes sense. So, it's time for some examples. An acyl cation, of course, highly electrophilic, a hard electrophile. So, a hypothetic reaction with a hard base let's have a look for a hard base. Hard base we have, for instance, an alcoholate. Should result in an ester, and we all know an ester is a rather stable compound. Of course, not alone based on the hard-soft interaction, but it has something to do with a conjugated system there. Yeah? So, but let's check, does the hard-soft acid-base principle, the Pearson principle, work out in similar cases? If we add a soft base, for instance, an iodide or a thiolate, well, what do we get then? A carboxylic acid, iodide, or such a thioester. Well, you can handle those iodides, no problem. But both compounds are far more reactive against hydrolysis with water, for instance. Now, an interesting argument is, what about the fluoride? Fluoride is clearly a hard base, harder than the alcoholate, and in that case we should discuss the stability of a carboxylic acid fluoride. Well, looks a bit suspicious to all of us. Yeah? And it was also a surprise for me to find that carboxylic acid fluorides are more stable against hydrolysis as carboxylic acid chlorides. So, acetic acid fluoride is more stable against the interaction with water hydrolysis as acetic acid chloride. Okay? Then carboxylic acid chlorides. Well, next type of reaction, a nitrile. A nitrile is regarded to be a hard electrophile. So, hard Lewis acid at the carbon center and a hard Lewis base with a free electron pair at the nitrogen. Plus hydrogen fluoride with the hard base fluoride here will react in an addition process and gives this iminium, this imine of an carboxylic acid fluoride, which of course will react with additional HF to form the iminium salt. So again, the concept works. Hard acid, hard base, also the other way round, hard acid, the proton, and hard base, here the nitrogen. The addition reaction works. Try that with hydrogen iodide and it won't work. So, now to a bit more interesting examples. Carbonyl compounds. The oxygen, hard base, the carbon is regarded to be a hard acid. Here we have a substrate which has an aldehyde functionality. And a tosylate within the same molecule. This carbon, a hard electrophile. This carbon with the tosylate leaving group is also an electrophile, also regarded to be rather hard electrophile, although somehow softer than that. Yeah? So, softer, not soft. Softer than this position. Here we have a thiophenolate. Thiolates are soft nucleophiles, especially if conjugated to an aromatic system. So, this is soft. And on the other hand, a cyanide as a relatively hard. Well, both are soft. Both are soft systems, but this is, of course, harder than that, or this softer than that. So, both soft, but this is relatively hard compared to the thiolate. And indeed, that thiolate selectively reacts with the softer position. Simply a nucleophilic substitution as an SN2 process. With the thionide, a completely different pathway, reaction pathway, is observed. It detects the harder electrophilic center. So that means we get this intermediate, and now an intramolecular SN2 process is observed with the alcoholate as the nucleophilic center and that carbon as the electrophilic center. Resulting in this product. So, enolates as ambident nucleophiles. Enolates with the two mesomeric structures. Of course, the oxygen is the hard nucleophilic center, and the carbon is the soft nucleophilic centers. That means the hard soft acid base concept suggests that hard electrophiles should form a bond to the oxygen, and soft electrophiles should form a bond to the carbon. So, is that true? As it turned out, it is somewhat an overinterpretation of the hard soft acid base concept. Because the enolate of cyclohexanone plus bromomethane in the gas phase has been tested to give exclusively the O alkylation product, although the methyl, the bromomethane, is regarded to be rather soft. This is somewhat contradictory to what we expect from the hard soft acid base concept. Another example is lithium enolates have been shown by the famous Dieter Seebach from Zurich University, who invented Umpolung of reactivity. He found that under the right reaction conditions, lithium enolates with acyl chlorides in THF at low temperature, minus 100 degrees to minus 80 degrees, react under CC bond formation, also contradictory to what we expect from the Pearson concept. And indeed, there are numerous examples known where normally the acylation takes place at the oxygen. Can easily form that. It depends on the reaction conditions. So, this is contradictory, or it gives the impression that it's contradictory to the hard soft acid base principle. But as I said, predicting this is soft and therefore it has to react here is an overinterpretation of it. You can use it as a rule of thumb if you make, for instance, a test reaction and you find with a bromide you have a certain product ratio. With the hard soft acid base principle, you can then predict how the product ratio will change if you change from the bromide to the chloride to the iodide or to the tosylate. So you need one experimental result to to make a prediction based on the HSAB concept. And this can be very useful. We will see that in a couple of more examples. A sodium enolate with a butyl compound, and X is a leaving group. We would anticipate two products, well, here cis and trans maybe. The O alkylation product and the C alkylation product. So let's form a table with percentage of O alkylation, and it depends very much on the solvent which is used. HMPT as a solvent, hexamethyl phosphoric acid triamide, First, with the iodide, just 15% O alkylation. With the bromide, we have more, 40% alkylation. The chloride, butyl chloride, is a more hard electrophile than the bromide. So we should get even more O alkylation. And indeed, that turns out to be right, 67%. The tosylate, 85. And then let's go to the fluoride, 96% O alkylation. The fluoride, butyl fluoride, fluorobutane, 1-fluorobutane is the hardest electrophile here. So it gives indeed the best yield of the O alkylation product, the best percentage. Right? Something wrong? No? Okay, it's okay. Good. Well, let's change to DMSO. Well, 10%, 23%, 46%. Well, here we have 44%, and the fluoride has not been tested. Generally, lower percentage of O alkylation. But HMPT and DMSO both are rather polar solvents. Similar, but this is much more polar. Let's go to a far less polar solvent, diethyl ether. Just 1% of O alkylation in the case of the iodide. Then 5 with the bromide, 18% with the chloride, and the tosylate, 20%. So, and well, okay, this means 80%, it's not a low yield, it's then 80% of the C alkylation. Generally, we can say that if we have dissociated enolates, naked enolates separated from the countercation by the solvent, which is indeed the case in HMPT and similarly in DMSO and maybe a bit also in DMF, then we have a high oxygen-carbon ratio. If we have ion pairs, well, then we will get an intermediate result. And if we have higher aggregates, as frequently observed in ethers as solvents, then we have a low oxygen-carbon ratio. So that means, or that shows, that the solvent has indeed a tremendous influence on the outcome of the reaction. However, again, if we have tested here, the bromide gives a 23% yield of O alkylation, and we want to increase the amount of O alkylation. Well, we know that we will get a better result if we go to the chloride or to the tosylate. But nevertheless, we could even more influence the outcome with changing the solvent. That's what we should learn from this example. Another interesting case is the alkylation of the enolate of acetic acid, acetoacetic acid ester. In this case, the potassium enolate has been tested in the reaction with ethyl halides, again in HMPT. In order to examine the influence of the leaving group on the ratio between O alkylation and C alkylation. So, X and the O-C ratio. Iodide, the softest ethyl electrophile which has been tested, 0.15. That means we have far more CC bond formation than CO bond formation in this case. Bromide, 0.65, we get more reaction, a bit more reaction at the oxygen. With the chloride, we already have the turnaround, more O alkylation than C alkylation. And then, consequently, with the tosylate, we get a rather high amount of O alkylation. So, now to organometallic species. So, where we have a carbon-metal bond. Methyl group sitting at a metal, then an ethyl group, an isopropyl group, and a tertiary butyl group. Those are all regarded as soft bases at the carbon center, but from the methyl species to the tertiary butyl species, they get softer. So this one is harder and this is softer simply because it is bigger and the anionic charge is stabilized through that molecule. One example. Although with this example one should be a bit careful. However, if we choose to let this react with methyl Grignard, we will get predominantly the 1,2 addition product. Changing to the isopropyl Grignard will give us predominantly the 1,4 addition product, or it's called conjugate addition product. Well, we have in that alpha beta unsaturated ketone 2 electrophilic centers. One of the carbonyl group, this is the hard electrophile, and this center, the conjugated one, is regarded to be the soft one. And well, you can interpret that in terms of the hard soft acid base concept. This is harder, reacts here. This is softer, reacts there. But maybe some, one has to, in the explanation, this is certainly not a good mechanistic explanation. You should take in the mechanistic explanation also into account steric hindrance, steric interaction, of course. Nevertheless, let's have a look at a similar reaction, cyclohexanone plus tertiary butyl lithium. This clearly gives this product. So, and this tells us that, well, the structure of the carbon nucleophile is less influential than the nature of the metal. Lithium is harder than the magnesium. So, hardness, lithium harder than the Grignard reagent, and this is harder than, well, any cuprate. Again, cyclohexanone. First, methyl lithium. Secondly, hydrolysis will result in the allylic alcohol, and while cuprate, for instance, this one, hydrolyzed after CC bond formation, will give the conjugate addition product. Until now, we have only interpreted this in terms of the hard-soft acid-base principle in focusing of the carbon center. We could also interpret it in focusing on the metal. Lithium, a lithium cation, harder than a copper cation, and therefore the lithium cation as a Lewis acid coordinates preferentially at the free electron pairs of the oxygen. It's already sitting there. Okay? On the other hand, the cuprate might preferentially coordinate to the electron density of that double bond. And indeed, Norbert Krause from our neighboring university, Dortmund, a couple of years ago, found some interesting examples, proved that with NMR spectroscopy, that the cuprates are indeed coordinating to that double bond. Two further examples for today. More complicated ones. An acylated pyridine, N-acylated, with a counter anion, presumably simply a chloride. So, where do we have electrophilic centers here? So, of course, this carbon is very electrophilic, and this is certainly the hardest electrophilic center. Here in this aromatic system, a conjugated system, we could write down some mesomeric structures with positive charge there and there and there, of course. This visualizes then that we have electrophilic centers here in the ortho position of a nitrogen and also in the para position. These in the conjugated systems are of course regarded to be much softer than that. Yeah? And well, okay, here and there we have a soft position, and there this is even softer. Okay? So, a reaction N-butyl lithium at minus 78 degrees was found out to react exclusively, almost exclusively, at this carbon. Well, this is in accord what we have already seen here with alkyl lithium species. And it simply set free the pyridine and formed that ester. Next test was done with a Grignard reagent and butyl magnesium bromide, also at minus 78 degrees. And here we observed predominantly the reaction at the soft and softer positions. What is the result in that case? This and the para isomer was found in the ratio 67 to 33. Of course, this means there is no real discrimination between the ortho and the para position, because we have the ortho position twice and the para position only once. It's just the ratio of 1 to 1 to 1, yeah, and this is the result then. So the organomagnesium discriminates between the hard center and the soft centers, but not between soft and softer. Going to a softer organometallic reagent, an organozinc, which is less reactive, and they have done the reaction at higher temperature, 0 degrees, and the copper, compound organocopper would react similarly. In that case, this case, they achieved a ratio of 19 to 81. That means with the less reactive organozinc, you indeed can discriminate between the soft and the softer position and get predominantly here the reaction in the para position. Last example for today. Once again, the enolate of a 1,3-dicarbonyl compound. In focus is the reaction with an allyl compound, an allyl electrophile. With the C-alkylated product as the target. First attempt simply with allyl bromide gave a 30% yield of the target compound. Interesting is the result with an allyl acetate, which is not reactive to this nucleophile, not that reactive to this nucleophile under moderate reaction conditions, but adding a catalyst, a palladium 0 catalyst, then this product was isolated in a 94% yield. Well, actually, this is the so-called Tsuji-Trost reaction. And the palladium 0 catalyst, as a very soft nucleophile, reacts with the allyl acetate, forming such an allyl palladium complex. And this is indeed a very, very soft electrophile, and this gives then a high yield. We will see more of these catalytic systems, of course, in summer semester. So, okay, I think we should finish for today. See you tomorrow with remarks on basic reaction types in organometallic, stoichiometric organometallics chemistry. Thanks for listening. See you tomorrow.